In this example, we are instructed to use the 5-step approach to graph the following polynomial equation. I'm going to encourage you not to use your calculator except to determine the relative max or mins. So my very last step is going to be to go to the calculator to find those relative max or mins. As far as the 5-step approach, here are the steps that we are wanting to use. First step is to use the leading term test to determine the end behavior of the polynomial. Second step is to determine the maximum number of zeros and turning points. Third step is going to be to determine the y-intercept. Fourth step is going to be to determine the zeros and their multiplicity. And what we will actually do in that step is write the zeros as x-intercepts. And then finally sketch the graph and then use the graphing calculator to determine the max and mins. Remember, one of the facts that we have learned about multiplicity is that if multiplicity is even, then the graph is going to turn around at that particular zero. And then if the multiplicity is odd, then the graph is actually going to cross through that zero. And this is a fact that we're going to use quite a bit when graphing polynomial functions. So first step here, leading term test. So basically we want to determine the end behavior. So in this example, look at the leading term, which in this case is negative x to the third. We notice that there is a negative value in the front and we have an odd exponent. And so the end behavior is going to be that the left-hand side goes up and that the right-hand side goes down. This is something that we know from prior lessons. The next thing is to determine the maximum number of zeros and turning points. So maximum number of zeros is always determined by the highest degree in our polynomial. Here the degree is 3, so that would be the same as the maximum number of zeros. The maximum number of turning points is always 1 less than that value, and so here maximum number of turning points is 2. Step 3, we need to determine the y-intercept. You might want to start this step. To determine the y-intercept, you will always substitute 0 in for x into our function. So basically let x equal 0 and evaluate the function at that point. So f of 0 equals negative 0 to the third minus 2 times 0 squared. Well, each one of these would yield a 0, and then subtracting them we would get 0. Here, because we're asked to find a y-intercept, then you want to make sure to write your actual answer as an ordered pair, so we would write it 0, 0. Now this is something that I'm going to box in later on. I'm going to come back and look for this point so that I will be able to graph that point at a later time. Number 4, we want to find the zeros. So to find the zeros, I would take the original function, and where f of x is, I would substitute 0. So I would have 0 equals negative x to the third minus 2x squared, and then I want to solve for x. Go ahead and go back and label. This is for finding the y-intercept, and this one here is for finding the zeros, so that later when you're looking back in your notes you'll know what to do for each one of these. Alright, solving this for x, it looks like we can factor out a negative x squared. That would leave us with an x plus 2. And then we know to find the zeros, we would want to set the x pieces equal to 0. Here the negative and the square doesn't make a difference on that first term, so the only way that would be able to be 0 is if x were 0. And then here, setting x plus 2 to 0, we would get x is equal to negative 2. Now these two values are what we would call the zeros. However, because we're actually wanting to graph, we want to write them in their x-intercept forms. So our x-intercept, the first one, would be 0, 0, and then the second one would be negative 2, 0. So based off of the zeros that you find, put the x values first, and then because it's an x-intercept, the second value would always be 0. I'm going to box those in. At a later time, I'm going to want to come back and I'm going to want to be able to see these points so that I can graph them. Okay, now another thing that I need to do is talk about the multiplicities of both of these intercepts or zeros. Notice here that the power on the x was to the second, and so this has a multiplicity of 2. Notice that we have an understood 1 on the power of the x plus 2 factor, and so this one would have multiplicity of 1. What that means over here is because the 0, 0 point has multiplicity of 2, that means that our graph would turn around at that particular point. This one, having a multiplicity of 1, means that our graph would actually go straight through that point. And that's something important that we need to make a note of. Okay, the last step is to actually sketch our graph. And believe it or not, from the information we have, we know a lot, but the only thing we don't know is max and mins. Okay, first thing we're going to do is plot any kind of points that we found. Okay, we found the y-intercept was 0, 0. So we'll plot that point. We found an x-intercept of 0, 0. That's the same point. And then we also have another x-intercept of negative 2, 0. Now, that's not a lot of information. However, if we come back up to the top, notice what we said the end behavior was going to do. The left-hand side is going to go up, and the right-hand side is going to go down. Also notice the multiplicity of our zeros. We know that we're going to turn around at the 0 of 0, 0. We know we're going to go through the 0 of negative 2, 0. So because we know the right-hand side goes up, we know the graph is going to have this behavior on the left side. Because we know the multiplicity of this 0, negative 2, 0, is odd, we know we're actually going to go through this point. And then at the other 0, we know that we're going to turn around there. So we don't know if there's a high or we don't know where the low point is here, but we do know eventually we'd turn back around, and when we hit this 0, we'd have to turn, and then the right-hand side would go down infinitely. So with the very little information that we know, because we know the multiplicities, and then also because we know the end behavior, we know the general shape of our graph. Now go, and using your graphing calculator, we are going to want to determine this minimum value. So plug in the original function into your y1. Let's scroll back up. Here's the original function that needs to go in y1. So negative x raised to the third, and then minus 2x raised to the second. Let's start by using just a standard window, and then we can adjust that if we feel like we need to. There's our graph, and you see it matches what we have down below. And then what we want to find is we want to find this minimum point. So do second, trace, minimum, press enter, and then when it asks for a left bound, we want to make sure to go to the left of that point we're looking at, press enter, go to the right, press enter, and then when it asks for a guess, press enter again, and then there's our minimum. Let's round to 1 decimal. So it would be x is negative 1.3 and y is equal negative 1.2. So come down here, and you don't have to be real exact about it, but just label that particular minimum point. This would be negative 1.3, comma negative 1.2. Okay, once we've done that, we have everything that we need. If you want to go ahead and label your two x-intercepts, that might be a good idea. You've got the 0, 0, and you have the negative 2, 0, but everything else is the way it should be. The ends are doing what they're supposed to. We have our relative minimum from the calculator, and then notice that because of the multiplicities, I'm turning at the 0, 0 here, and then this multiplicity, I'm going directly through that particular 0. So all my work matches up with my graph, and I have what I need. Now, on this kind of problem on a test, I will be mostly grading that you are doing the correct work up here to get the correct graph down here. I realize that your graphing calculator will give you the graph, but that's not the thing that I'm most interested in.